So to get the transfer function for the Allen key circuit, we got these components for the resistors and the capacitors, and then here is a little diagram of the Allen key we used. Here is the formula for the transfer function, and then we just subbed in the values and we ended with a transfer function of this. To finish it off, to get the frequency response of the transfer function, you just sub in JW for S.
Okay, so now we're going to build our silent key filter in LTSpice. So from this Japanese website, it gives us our circuit diagram, and then we can also find our resistor and capacitor values. So our cutoff frequency was 1000 Hertz. Our damping ratio was 0.25. So if we go down and click calculate, it should give us appropriate values for a resistor and capacitor. So here we go. However, in the lab, we didn't have 13K, and we also didn't have a 4.3K. So we just switched them out to like similar values which you do have. So we just replaced this one with 12K and this one with 4K. We did have a 0.1 microfarads and 4.7 nanofarads, so that's grand. So if you just go back, you can just type in the values that we do have. So 12K, we had a 4K there, and then this one was 0.1 microfarads. This one was 4.7 nanofarads. And if we hit calculate, it should give us similar values for the car frequency and damping ratio as before. Yeah, so our car frequency is 1059 Hertz, that's grand. And our damping ratio is 0.25, that's grand. So now we can build this in LTSpice. So if you open up LTSpice here, so we need a resistor, there, and another one there, and then we need capacitor, so one there, and then another one here. Then we need an op amp as well, so a universal op amp works best for me, so I'll just use that. Just whack that there. Oh, okay. And there. So that's ground. So now we just connect some sub wires. And then there. And put that there. And then this negative input is going back around to the output of the op amp. So that'll go there. And then this capacitor here is connected from here to there. And then back here. Okay, and then we're gonna put over here, we're gonna put a voltage source and pass a step through that. So if you just get voltage, so one there. Then we're gonna ground them two, the capacitor and the voltage source. So ground there and the ground there. And then we need to power up the op amp because we're using the universal one. So if we just put a wire from here to there, and then get a few voltage sources in there. So voltage source there, and one there, and then just connect them up. So that go there, this goes there, this goes there, this goes there, this goes there, and then we just need ground in between there. So okay. So now let's just put in our values for the resistor and capacitors. So R1 we said was 12K. R2 we said that was 4K. And then okay, and then our capacitor here, C1 we said that was 0.1 microfarads. And then C2 here was 4.7 nanofarads. And then let's power up the op amp, that would be nice. So 15 volts here. And then let's just say another 15 volts here. Grand. Okay, so now we just need to we're going to pass a step through the circuit. So if you right click the voltage source, click on advanced, and then change this to a pulse, you can pass a pulse through that. So initial voltage is 0, let's just say 1 volt for the voltage on. Delay for 1 second. Key rise, let's say 0.001, make that really small. Fall for 0 seconds. And then let's make it on for 2 seconds. It has a period of 4 seconds. And let's just do 1 cycle of all that. So, okay. So now if you run it, so run. Stop time, let's make it 3 seconds. Okay, so now if we go to the input here, we should see our step. Yeah. So that's our step that's going into the circuit. And then at the output, we should see the step response. Yeah, so that's the step response there. So if you zoom in, you should be able to see the oscillations. Yeah, so there's the oscillations there. So that means it's a second order system. So that's handy. And from this, we can actually bring that into MATLAB and analyze it even more. So we can just make a simple WAV file. So spice directive, and then let's just make it into WAV file. So dot wave, and then let's save it. Let's just save it somewhere. Yeah, here's ground. So, C copy paste, and then put that there, and then let's just put it into an op.wav file. Yeah, it's 16 bits and a sampling rate of 16,000, and then it's at node. Output's at node 2 or 3. I think it's 3. We can just check that here. Oh, it's node 2. Okay, and then change that to 2. Okay, so now if we run it again, so just make sure. So the input here is a step, yeah. And then if you go to the output, it should be the step response. There we go. Okay, so now that we run it, it should be in this WAV file that we saved. So we can bring that to MATLAB. So if you just go to MATLAB real quick, there, and then open up the folder to where it's saved. So yeah, sign 5, yeah, that's there. Yeah, so it's over there, op.wav. So we can just bring this into MATLAB. So let's just say step response fs, sampling frequency, is equal to audio read op.wav. Okay, and then so that's put in MATLAB there. So let's just make a time vector so we can plot it against time. So 0 to length of step response, and then -1 bracket divide by fs, grand. And now we can plot it. So plot t against step response, grand. Okay, so that's the step response there. However, it kind of stops at 1, at amplitude 1, because that's what our voltage on was set to as an LTSpice. If you zoom in though, you can still see the oscillations, but they're all like half, they're all cut off. So that's not really good. But we can change that in LTSpice. So if you just go back to LTSpice and then change this to something that you can see in MATLAB. So let's just change voltage on to 0.5. So that's ground, and then run it again. Yeah, so it's still oscillating here if you zoom in, but it's oscillating at 500 millivolts this time because we changed the voltage on. So it's still oscillating though, second order system. So if we go back in MATLAB, we can see that. So just run all those commands again. So there we go. So now this should work and show us the step response. Yeah. So if we zoom in, that's the step response there of the second order system that we just had in LTSpice. You can see it's oscillating at 0.5 volts. So that's it there. So this X label would be the time in seconds. And then the Y label would be the amplitude. Yeah, so that's the step response there. Look it is.
Okay, so this is the MATLAB code section of the assignment. We're gonna start off with step response with fs, which is the sampling rate, which is 16,000. We're gonna audio read the vout.wav, which is the output file of the LTSpice. We're gonna get the time vector, so t is equal to the so 0 up to length step response minus 1 divided by fs, and then we're gonna multiply the step response by 10, because in our LTSpice the step response only went up to about 150 millivolts, and we wanted a little bit larger on the MATLAB, so that's why we increased it by 10, and that gave us an output of 1.5, near 1.5 volts. And then we're going to use this function figure, which is basically allows for plots. It can allow for multiple plots on the plot command. So we're just going to plot t step response, x label time seconds, y label amplitude, title step response, and grid on. And this is the first one that comes up. So as soon as time hits 1, increases up to near 1.5 volts, and if I can just zoom in onto that, this shows the oscillation of the step response when it quickly reaches steady state and steady at 1. So we're going to move on to the next one, impulse response. So we're going to do diff step response. Diff gives a sequence that resembles the impulse response, and then we're just going to get the impulse response, the FFT of impulse response, and then we're going to get the ABS of that, which is just the magnitude, and we're going to equal that to x. So again, figure, plot x label frequency index, y label magnitude, title FFT of impulse response. We're going to turn on the grid again, and this is the next one. So yeah, there FFT, double-sided spectrum, and that's it of the impulse response. And then we're going to move on to the next one, which is just the length of x. So plot x length of that multiplied by fs, which is divided by the length x minus 1, which we're going to call fax. We're going to use figure again, plot fax and x label frequency, y label magnitude, title frequency response. Xsim, we chose 0 up to 100 hertz. It doesn't really matter, we could choose 0 up to 10. We're going to turn on the grid, and then let's just open this up. Yeah, so it starts at 1 over here, and as the frequency increases, the magnitude increases, but very, very small. It's extremely small. This suggests that it's a low pass filter. And then we're going to move on to the next one, figure, so semi-log x, fax, 20 log 10 x, x label frequency, y label magnitude in dB, title logarithmic frequency response, and then we're going to turn on the grid again. So let's just open this up. So this section here, the one I'm circling here, this section is correct, and this one that I'm circling here is incorrect. The reason for this occurring is due to the FFT, which just causes this to occur. But if we look at the increase in dB here, it goes up to about 6.3, 6.4 dB, and then drops down to about minus 16 dB per decade after that. That's it there. Then from here, we're going to use our components, so our component values that we used. So R1 was 12,000, R2 was 4,000, C1 was 0.1 U, C2 was 0.4 NF, and then our time constant, so tau is equal to R1 times C1. We're going to display 1 over tau, which came up to about 833.33. We're going to display 1 over 2 times it by pi times it by tau, which came up to about 132.63. We're going to get the transfer function. So the transfer function using BA coefficients. So B was equal to this number, pretty large number. A was 1, 333.33, and then this number again. And then we're going to get the SYS1, which is just the step response of the transfer function. So, we're just going to call it SYSS1 or SYS1, and we're going to use TF function, which is a transfer function, BA, just the coefficients, and then once we get the figure step of the SYS1, we're going to title step responsive transfer function, x label time in seconds, y label amplitude grid on, and this is the step response of the transfer function here. And yeah, as you can see, it goes up to near 1.5 there, and it eventually reaches steady state. Then we're going to get out of that. Figure, again, Bode of the SYS1, title Bode plot of the transfer function. So we're going to open this up. Yeah, and it shows 0 dB up to 6.3, 6.4, and then it drops down. And as you can see, the phase starts off at 0 and it phase shifts down to about minus 180 degrees there. And then we're going to go H and omega, which is omega is the angular frequency, H is the frequency response values. And then we're going to use freaks with S, which is just used for continuous time systems. And we're going to use B and A again. We're going to figure omega ABS H, ABS just the magnitude of it. X label frequency, Y label magnitude, tidal frequency response, freaks, and then grid on. And we're just going to open this up here. And this is just the frequency response of the transfer function.
Okay, here we have the input voltage, which we inputted 9 volts into the VCC port on the op amp, and then in this pin, in the ground pin, we have the negative voltage, which is used to display the AC signal on the oscilloscope. Okay, so this is the signal generator, which sends the signal into the breadboard. It is also connected onto the channel 2 here, which displays the signal on the oscilloscope. Then we have the output, which is connected from the op amp, which displays the output signal on channel 8. Alright, so here we have a Bode diagram of the magnitude and the phase, and we're comparing it with what we got on the oscilloscope. So we have to get 4 different values. The first value we're going to get low frequency. So we went with around 24 Hertz, and then you can see there's no magnitude difference or phase shift on it, so it's, according to this, it's pretty correct. The next value we're going to use is a 1 kilohertz, and then we can just change it on this. Scale of it. Let's get it to look like that. Now on the Bode diagram here, it's supposed to be double it. Unfortunately, we didn't get that value, but it could be due to numerous amount of factors. But we can also see the phase shift of around minus 80, which you can see it's pretty accurate according to the oscilloscope. The next value we're going to use is 2 kilohertz. So as you can see here, it's supposed to attenuate by roughly a factor of 10. So we can go over here and change it to 2 kilohertz. And we can also see a phase shift of, according to this, roughly minus 160. So change the scale to make it more visible. So it's almost 180, which again is quite similar, but attenuating by a factor of -10. It's maybe not exact, but it's close enough. It's attenuating. And then the next value we can use is a much higher frequency, so we can just keep going up, and basically what we're expecting to see is it continuously attenuating. And then the phase shift also gets more, stops at 180. Alright, to get the step response of the signals here, the first step that you must do is change it to a square wave. After that, then you can narrow down the frequency till you get something looking like that. And then if it's still not kind of clear enough, you can change the scale. Change the scale to make it so you can see it a bit more.